Hi everyone. Hope you're all doing well. I see we just are waiting on one person, so let's give them a minute to come by, and if not, I'll get started. I do have some announcements to make at the start, so I will do that momentarily. There we go. Okay, so welcome everyone. Like I said, I just have a few quick announcements to make. Then there's a couple things we might want to chat about, and then there's some questions. If you have any questions, I'm happy to address them. So first off, it's not going to be all 4 of these. That would be too much for the homework assignment. You see how it says chapter 5, 2, 4, 6, 8. It definitely will be 2, and then I'll choose one of the others. So just stay tuned for that. I'll get that to you tomorrow, along with the data sets and the probes for each problem. So it'll be just like it's been in the past. In other words, you have, 2 problems, A and B. I think that's enough to give you the exposure I want to give you to our next set of tests, which is one-way ANOVA and Kruskal-Wallis. And then you can see I've given you some reading to look at in Laird. We're actually going to go through a fair amount of it today for one-way ANOVA and Kruskal-Wallis. Not all of it, but a fair amount. So hopefully that will actually cut down on the amount you actually need to go through there. In other news, I'm pretty sure I did this. I think I wanted to send you an email last night and set it up to send and then didn't send it. So I think some of you know this, but in case you didn't, I apologize. The reason there was no Dropbox for the dependent samples article for non-presenters is that we've decided to take a pause on that until next week. So if you already did it, it's one less thing for next week, I guess, but I apologize in that you might have wanted to apportion your time differently. So dependent samples, and then the Wilcoxon will be the articles on tap for next week, and we'll talk about both of those next week. As always, if you have questions on the articles or, want some assistance, just, reach out. Either grab a time using my OneTub, or if those times don't work for you, then just go ahead and ask me and we'll set up a time to work together. Next thing I want to talk about is the exam. And I will have that graded by tomorrow. I got part 1 done, of course, and part 2 is about halfway done. So I just need to finish that off and get you actual grades on it. But if you'd like, what we can do is either together or separately, we can actually go through the exam and talk through like what the solutions might have been. I think for the one that was the one that's written out, sorry, let me try that again. It was number 4 on part 2, and it was the one where you had to identify the errors. I think for that one, I'll just kind of go through and show you all the different ones that were errors. So I'll either do that speaking to you or in writing, however we decide to do that. So like I said, I'm happy to take, if that's something you want to do, I'm happy to take out some time maybe in the second part of today and go through go through the exam with you. That's definitely something we can do. So that brings us to today's topic and how we want to approach that. So today, as you can see, we're moving on to the one-way ANOVA and the Kruskal-Wallis. And the one-way ANOVA you may have heard of, but it's basically for comparing 3 or more different groups. So it's really just like the independent samples t-test with a tweak. Because with the independent samples t-test, we could only compare 2 groups, people with blue eyes, people with brown eyes, and that sort of thing. Now we can add in a 3rd group, people with blue eyes, people with brown eyes, people with green eyes, people with hazel eyes, whatever we want. So we can have as many groups as we like with the one-way ANOVA. We're only limited by our sample size. And the Kruskal-Wallis is going to be the non-parametric version of that. Okay, so having said that, the other thing that's come up this past week is basically how we want to structure the class to make it most useful to everyone. And I think for some, it's maybe it's maybe a challenge, I guess I'd put it as. It's a challenge to, listen for these, long periods of time, and maybe it's easier to do it on the recording and that sort of thing. Oops, sorry, I didn't mean to do that. So what I've done for today is there's only the first 29 slides, 28, 29 slides are theoretical. The rest is all going through either layered or doing exercises in SPSS. So I'm hoping that improves your take on it. But having said that, I think it's useful to be here, but I'm also not going to. If you find that this is just not as helpful after today, and you'd rather just listen to the lectures on your own, I mean, I'm okay with that. Maybe we can talk about it beforehand. But if that's how you'd like to approach it, I'm okay with that. But just give me maybe a heads up, so so I'm not waiting for you when we actually, go through lectures. Okay, so that's a lot, but it's all the stuff I wanted to share with you. So I do want to, start in on ANOVA and Kruskal-Wallis today. I do want to, of course, give you a break, as we always do. We'll do the theoretical stuff. It's not too bad this time. There's less theoretical stuff now that we're into the tests, and more just SPSS and understanding the assumptions and those sort of things. So maybe let's start with that, and then I will see where we want to go kind of post break. We can check in and see what people want. But if there's any questions or anything you want to share right now, please feel free to chat in. You are always welcome to, since it's such a small class, you can come off your mute as well. It's just always the risk that you're talking at the same time as someone else, but it's a relatively low risk since it's such a small class. So if you have anything, please feel free to let me know, and otherwise let's get into it. Okay. Well, no one's unmuting right away. You might be chatting in, and it might be a longer thing, so it might be taking you time. So I'm going to kind of get started, but if any chats come up, I can always stop and take your chats at any time. So slideshow, let's do this. Okay. So as I already said, the layered, we're going to go through some of it today, and the homework will only be 2 of those 4. So I will keep you posted on that. Okay. So as I said before, this is kind of a new research situation, a new research design, if you will. If you are looking to compare, let's say, psychology majors, physics majors, and math majors in terms of their level of happiness, then we can't use any of the tests we've discussed so far, since we now have 3 levels of major, 3 different types of major that people could have. So what are we going to do? And you might be wondering, well, why not run multiple t-tests? Why not take that independent samples t-test that we've already learned and already are starting to hopefully feel comfortable with, and just run that several times, right? I can compare group A to group B and group B to group C and group A to group C. I can make it work. The problem is that your chance of making a type 1 error increases. So we don't like type 1 error, if you remember. We're really opposed to it. So instead, we're going to use a new procedure called analysis of variance, or ANOVA. And ANOVA helps to control this type 1 error by testing all the means at once. Okay. So the big question, or one of the big questions of ANOVA, is where does the difference lie? So let's say we run our ANOVA and it tells us, yay, you found significance, you found something, there's a difference here. Then you might ask, well, where? Between the psych majors and the math majors? Between the psych majors and the physics majors? Between the physics majors and the math majors? Is it between all of those? Is it between one major and the other majors? And that's what we'll be finding out using our analysis of variance, along with some post hoc or after tests that we want to run after we run the main ANOVA. Okay. So when we're running that main ANOVA, the key question is there more variability between the groups or within the groups? And we're hoping for between. Because if the alternative hypothesis were true, if we were to reject the null, it would mean that there's more variability between the groups than within the groups. And I'm actually going to show you, I'm going to have to turn on the computer sound for a second, because I'm going to show you in a moment a cute video that I think explains this well. I think I've shared my computer sound. So an alternative hypothesis in ANOVA is that there's at least one difference between the groups. So in other words, if there's only a difference between our math and psych majors, and there's no other differences, math and physics are the same, physics and psych are the same, if it's just between math and psych, that's still a reason to reject the null. You still get to reject the null. So let's look at this example, and then I'll show you the video example. So let's consider learning performance under 3 temperature conditions. Okay. And we see that under condition 1, where it's 50 degrees, and we have 1, 2, 3, 4, 5 people, and we see that their average was 1. They got 1 problem right. Then we have the group that got the 70-degree temperature. They got 4 problems on average correct. And then our final group that has the 90-degree temperature, they also got on average 1 problem correct. Okay. So what does that mean? Well, if we were doing an ANOVA, we'd actually test all this and look for significance and look for differences. But just eyeballing it, I would say it looks like treatment 2, the 70-degree group, performed much better than the 50-degree group and the 90-degree group. And I would also be willing to wager that there's no difference between the 50-degree group and the 90-degree group, since they had the same average. Okay. So again, you could, if you're comparing 3 groups, you could have 1 difference, you can have 2 differences, you can have 3 differences, and of course, you can have no differences. That's another possibility as well. Okay. All right, so now I want to share this video with you. The sound is not the best in terms of his speech, I guess, is a little bit gravelly, if I remember correctly. But I think it's still very worthwhile to look at this. So, oh yeah, I thought someone had gotten knocked. Okay. So let me see if I can play it straight out from here. I'm hoping I can. Oops, no, behave. Try that again.
Let's say you want to find out if the beverage that people drink affects their reaction time. So you set up an experiment with 3 groups of people. The first group gets water to drink. The second group gets some sugary fruit juice. And the third group gets coffee. Now you test everyone's reaction time. And you want to know if there's any difference in reaction time between the groups. The null hypothesis says that the mean reaction time for all 3 groups is the same. If there were only 2 groups, you could use a t-test to find out if there's a difference between them. But when you have 3 groups or more, you need to use a different approach, the analysis of variance. When you do the experiment, the scores won't all be the same. The total variation of all the scores is made up of 2 parts. The variation within each group, because the people in each group have different reaction times, and the variation between the groups, because the drinks you gave each group are different. Here's an example. Look at this set of scores. They've been sorted into order to make it easier to see the patterns. You can see that there's a lot of variation within each group. Some people are faster and some are much slower. But all the groups look pretty much alike. There's not much variation between the groups. In this case, you'd say that most of the difference is due to the people, and the drink didn't make much of a difference. You would accept the null hypothesis, that the type of drink doesn't have any effect on reaction time. Now let's look at a different set of numbers. In this case, all the scores within each group are very close to one another. There's not a lot of variance within each group. But the groups are very different from one another. There's a lot of difference between the groups. In this case, you would reject the null hypothesis. In this case, the type of drink makes a big difference. So here's the idea behind analysis of variance. Figure out how much of the total variance comes from the between groups variance and the within groups variance. Take the ratio of between groups to within groups variance, and the larger this number is, the more likely it is that the means of the groups really are different and that you should reject the null hypothesis. In the examples, it was obvious where the variance was. Now look at these numbers. You probably can't tell if there's a significant effect because it's not clear whether there's more variance within groups or between groups, or how much. The calculations show that the ratio is 4.27, which has a probability of 0.04, so in this case you can reject the null hypothesis. With these numbers, the drink you give the people does have an effect on their reaction time. What's that 2,12 doing there?
Okay, so we'll actually review together how you actually look at the 212 and the 4.27 and those sort of things. Or if you like the video, you can always go back and play more of it. But I just wanted to share that main point with you, that it really how you discern between groups difference and within groups difference. So that was my main point. Okay. So again, that between groups or between treatments, you might see it referenced in like some old articles like that. Variance is the variability that results from differences between the sample means for the levels of a factor. In other words, like we just said, between the groups, between the water, juice, and coffee. Within groups, variance is the variability within each sample, within each level of a factor. And that really has to do with the person, the individual differences within a group. So how much do the people drinking the water differ from each other? And how much do the people drinking the juice differ from each other? And how much do the people drinking the coffee differ from each other? So that's the idea of between and within groups. Okay. So when we think about that total variability, that between groups and within groups, the between groups, as I already said, is the good stuff. It's what you want because that contains the group effects. Of course, not surprisingly, it also contains some possible chance or error, whereas the within groups, we consider that all error. Okay, at least according to our calculations and how we think about this. Okay. So the ANOVA test is also called an F test. Before we had T, now we have F. And really, the point of this slide is to show you that there's really not much difference between the T and the F test. It's really still looking at what's going on between the sample means on the top and what's expected by chance on the bottom. Okay. So the difference between sample means is quite easy for two samples. So if you have one group that's 20 for their mean and another group that has 30 for their mean, then the difference is simply 10. But once you get that third group with a mean of 35, the concept of differences between sample means gets tricky, and that's why we sort of go over to this variance notion. Okay. The assumptions for a one-way ANOVA. Very similar to independent samples t-test in that we have independent samples, normality, and no significant outliers. Okay, so again, we have independent samples, normality, and no significant outliers. We're also gonna, just as with the t-test, the independent samples t-test, we're gonna look at homogeneity of variance, but that doesn't tell us whether or not we can do the ANOVA. It just tells us which kind of ANOVA we're gonna do, just like the t-test told us which kind of t-test we're gonna do. So this lines up again very, very similarly with the independent samples t-test. Okay. Okay, so in terms of the one-way ANOVA, we have these different sums of squares, and we're not going to get into a whole bunch of detail, but I just want you to be able to read the output easily enough. So I'm going to share just a little bit with you about sums of squares. There's going to be a sums of squares total, which essentially is the sum of the sums of squares between and the sums of squares within. So this is just a prelude, if you will, to getting that between groups variance and that within groups variance. It's one step before we actually get to that. Okay, so in addition to sums of squares total, sums of squares between, sums of squares within, we're actually also going to have degrees of freedom, which we've talked about before, for total, between, and within. And then a new symbol, which is mean of the squares. That's our actual variance. So MS technically stands for mean of the squares. And it's our actual variance for total, between, and within. Okay. So let's actually look at an example together to better understand just how this is laid out. So we have some new research, well, it's not so new anymore, but there was some new research suggesting that watching television, especially medical shows like Grey's Anatomy, House, there's a lot of medical shows on these days too, can result in more concern about personal health. So some surveys were administered to college students measuring television viewing habits and health concerns, such as fear of developing the diseases and disorders seen on television. For the following data, students are classified into 3 categories based on their television viewing patterns. Okay, so we're going to have people who view it not so much, kind of a bit, and a lot. And then we're also going to look at their health concerns that are measured on a 10-point scale with 0 indicating none. Okay. So here's the setup of our one-way ANOVA. We have our different television viewing groups, little or none. So these are people who don't view much of those health shows, moderate amount of those health shows, and a substantial amount of those health shows. And then here is their health concerns ratings. Okay, so we have the perfect setup for a potential one-way ANOVA because we have 3 different groups here and we have some continuous dependent variable looking at health ratings. Okay. This is how someone might talk about some of the data associated with this. They might talk about the sample size, and we can see there's 10 in each group. They might talk about total scores for each group, mean scores for each group. And the mean is a little bit more interesting than total. We can see that the mean's kind of increasing over time, over groups, sorry, between little, none, moderate, and substantial. And then some sums of squares like I was just sharing with you. Here we have the total n, which is 30. So this now sets up, or this is an example of when I said before that we use lowercase n for sample and capital N or uppercase N for population. This is an exception to that rule because we would use, in this case, it's more typical to use lowercase n for the individual samples and uppercase N for the total sample size. So that's one difference you may see out in the literature. Okay. This is just for the interested. This is not something I would ever expect you to calculate or do, but I just wanted to share with you how the formulas come to be that actually, and I didn't share the SS since that's kind of a bigger formula, but I did share the degrees of freedom, which is really just the number of groups minus 1. So it's what we're used to in a way. N minus k is the number of people minus the number of groups, and n minus 1 is the number of total people minus 1. And you can see the division here that we take our sums of squares over the degrees of freedom to get our variance. And then we take our 2 mean squares to get our F, which we talked about. The F is the final, the good thing we're looking at. But like I said, that's just if you're interested in that, in knowing that or want it for reference. Okay. So here's an example of what you might actually see, and it'll look slightly different in SPSS, but this is the idea. You'll see sums of squares for between, for within, for total, same for degrees of freedom. You'll only see 2 MSs, 1 F, and finally a p-value. And it might be an exact p-value. That's what we've been primarily doing, is reporting exact p-values. That's what you'll see in SPSS. Sometimes in articles, people will just report a p-value. P is less than 0.05, meaning, yeah, alpha was 0.05, p is less than 0.05, I'm good, I met the criteria. Or if they want to get fancy, they might report, if their alpha was 0.01, they might report p less than 0.01. Sometimes in an article too, as opposed to saying p, you could say p greater than 0.05 if again 0.05 was your alpha. But people sometimes use just NS, and NS stands for not significant. So if they don't even want to report that, they can just say, comma, NS, this is not significant. Okay. So let's look at one more example together. Binge drinking on college campuses has been a hot topic actually for quite a while in the media and in scholarly research. And these group of authors reported the results of a study relating perfectionism to binge drinking. So in this particular study, students were classified into 3 groups based on the number of binge drinking episodes they experienced during the past month: 0, 1, 2, or more. The students then completed a perfectionism questionnaire, including 1 scale measuring parental criticism. Students rated their level of agreement with each item, and the total score was calculated for each student. Again, that's for that perfectionism scale. And the following results that I'm going to share with you are similar to those obtained by the researchers. So if we have an alpha of 0.05, we want to know, is there any difference between the groups? Okay, in the last setup, since P was less than 0.05, we could conclude there was a difference between the groups. Let's see what happens here. Okay, so here's our setup. Here's our initial data. All right, so again, these are the binge drinking episodes in the past month, 0, 1, 2, or more. And here is their score on that perfectionism scale. Okay. Once again, here's some summary information of the kind you might see out there. Sample sizes, total sample size of 15. Means, once again, we see an increasing trend here across the binge drinking episodes, and some sums of squares. And again, I wouldn't worry if the sums of squares doesn't make much, doesn't really have much meaning for you at this point. It's mainly as long as you can pick up the mean, pick up the sample size, and the total n, that would be great. Okay. And here is the result. So here we have sums of squares, degrees of freedom, MS, F, and finally our p-value. P is less than 0.05. So again, just like in the first example, we know we have significance. We know that there is a difference somewhere between the groups. We just don't know where yet. We just don't know if there's multiple differences, or if there's one difference, or what have you. Okay. So this significant ANOVA tells us that there's a difference somewhere between the groups, but not where. So to figure out where, we need to run post hoc or follow-up tests to figure out which groups are different from each other. Now, one very popular test when you run an ANOVA is the Tukey's honestly significant difference test. Now, the name probably sounds a little bit funny. It's actually often called Tukey HSD as well. And the reason is that so many different people have tried to create, for their own research and statistics, a good post hoc test, that people have come up with sort of these competitive names around it. So Tukey, or John Tukey, came up with the name honestly significant difference test, so this is a good one. So anyway, just that's a piece of trivia for you. And it gives the ability to compare differences among the means. So it gives us this ability to actually see where the difference might lie. Now, there's another test that we're also going to look at for post hoc, and that's a Gaines-Howell. And we're only going to look at that one, though, if we fail the homogeneity of variances test. So we'll get into that a little bit later. But so Tukey HSD is certainly not the only game out there. It's one of the popular ones, especially for your straightforward ANOVA. Okay. So here is yet another example of a one-way ANOVA F-test, and here's how it looks in SPSS. Pretty similar to what I showed you before, with an exact sig value. This is actually a setup of a fear of spider example, and it took people who were afraid of spiders and gave them one of 3 kinds of treatments: systematic desensitization, hypnosis, or no treatment. And then they wanted to see if there was any difference between these different kinds of treatments in addressing the spider phobia. Okay. So this is what a Tukey HSD looks like. And this is the only output that I really want to make sure you're good on in terms of understanding. So I want to go through it and walk through each of the steps. So basically, I want you to think of this as 6 lines, 6 rows of information. The first row is going to compare none to systematic desensitization. The second row is going to compare none or no treatment to hypnosis. The third row compares systematic desensitization to none. Well, didn't we just do that? None and systematic desensitization. This is systematic desensitization. None. Aren't they the same thing? Yup. And you'll see that the numbers are going to be very much the same. And the sig values will be exactly the same, which is our main concern here. Okay, so finally then in the fourth row, we get to systematic desensitization and hypnosis. The fifth and sixth row are repeats. You don't need them. So really, when we look at this kind of setup for comparing 3 different groups, we're interested in the first row, second row, and the fourth row. The rest we don't really care about. I mean, it's fine to look at them, but they're repeats. So now that we know that, let's start walking through. None and systematic goes all the way over here to our sig value of 0.002. And we say, look, that's significant. There must be a difference in systematic and none. Okay. And actually what they're really doing here is they're subtracting none minus systematic, or I minus, this should be it often doesn't show up, but there's a theoretical J here. And we can see that there was way more symptoms after the treatment, if you will, in the none group than in the systematic group. So the systematic outperformed the none group because there were less symptoms after the systematic desensitization. Now, if you don't like doing that subtraction business, don't worry. You can also get nice descriptives out of the output that will tell you exactly what the means are for the different groups. Okay, so that's not a problem. And then this tells you, like we talked about, there is an important difference, and it seems like systematic outperformed none. Now we go to none versus hypnosis. Go over to the sig, 0.659. That's certainly greater than 0.05. No significant difference. No important difference there. So none and hypnosis performed about the same. And then finally, we come to our fourth row, systematic and hypnosis. Go over to the sig value. It's 0.025. That is less than 0.05. So once again, yes, there is an important difference between systematic and hypnosis. And we can again see that systematic outperformed hypnosis. And we would see it better if we wanted to look at a descriptive, descriptives that gave the means. Okay. All right. Okay. So in terms of interpretation, we're pretty much doing what we did before. If the observed p-value in SPSS is less than alpha, it's likely to be statistically significant, and we're likely to reject the null. If the observed p-value is not less than alpha, it's not statistically significant, and we do not reject the null. Now, here's an exception to the rule, and an interesting one. I want to talk it through with you a little bit. With the t-test that we've been looking at, with with other pieces, we always said if the results are in the opposite direction of what's stated in the alternative hypothesis for a one-tailed test, we're not going to reject the null. That is true. That's always true. However, in the case of ANOVA, we're not going to get that deep into custom contrasts where that would be an issue. So in other words, we're not going to really get too concerned about one-tailed tests as we look at ANOVA. That doesn't mean you can't have a one-tailed test when you look at ANOVA. It's just for the purposes of this class, we're not going to get that deep into it. If for your dissertation you wind up with a one-tailed ANOVA, there are ways to attack that and ways to work with that that are actually shown in Laird. So don't worry about that, but we're not going to get into those weeds right here. So the reason is it's usually when people are talking about, and I'll look at this chat real quick. Okay, so we don't need to divide by 2 for these. Yes, that's true. You don't need to divide by 2 for these. So the reason is usually when we talk about more than 2 groups, we don't make these very specific alternative hypotheses. You could say that psychology will outperform math, and math and physics will be the same, and psychology will outperform physics. That's how you'd have to phrase it to have all these one-tailed hypotheses flying around, right? And we generally don't do that. We generally, go for it. There'll be a difference in these 3 groups. Okay, so that's why. But like I said, if you have a different experience, I'm always happy to answer questions either later in the class or, the next year or something. So don't worry about that. Okay. Mind blown. Okay, so let's look at this real quick. For 2 independent samples, technically, you could use either the t-test for independent samples or a one-way ANOVA. It'll always result in the same direction because it just so happens that F equals t squared. Now, that is a special circumstance where you have an independent samples t-test. You have, sorry about that. You have an independent samples t-test that actually meets all the criteria and you can run it, or versus a one-way ANOVA that also meets all the criteria and you can run it. Then in that case, t squared equals F. So if you ran on the same data an independent samples t-test, got your t-score, and then you ran the F, and if you took both of those results and you took the t and you squared it, you would get the same as you got for your F, for your one-way ANOVA. So I always like to share that because I think it's common to think of these tests as so in their own individual buckets and categories, and they're more related sometimes than we give them credit for. So there's a lot of relationships between these tests. And I think it's helpful to recognize that and recognize that they're not so different than when you're trying to understand them. Okay. So what we're going to do next, and this is a question point for you guys, and I'm actually hoping that this is big enough on your screen, but what I'm going to do is I'm going to walk you through some of what Laird does to actually compute an ANOVA. So if you're not seeing this easily and you prefer me to go over to Laird so that I can tell you what page to go to and we can both work through Laird, me here and you on your own screen, let me know, please. Otherwise, I'm going to use this. Okay, all right, so I'm going to use this. If you missed that and you want to tell me in a moment or so, I can still change, but I'm planning to use this. So here's how we get our one-way ANOVA. We go to, well, before we get our one-way ANOVA, how are we going to actually figure out if we're going to run a one-way ANOVA? So you're going to do the same thing that you've done for the t-test for independent samples. Okay, you're going to go to descriptives, analyze, descriptives, explore. Under plots, you're going to make sure you check off that normality plot with tests. And you're going to look at the results from your explore. You're going to see if it passes the Shapiro-Wilks test, just like you've been doing. And then you're going to look at the box plots and make sure you don't have any significant outliers. Okay, so that if you pass those tests just like you have before, then you get to run the one-way ANOVA. So that's what we're going to look at now. Okay, so it's basically the same exact setup. And this is nice because, you know, with the t-test for dependent samples, we had to do the diff thing first. We don't have to do that because we're back in comparing groups. Okay. And of course, design-wise, you do want to make sure your groups are independent from each other, right? So for comparing eye color, and we've got brown eyes and blue eyes and green eyes, just for the heck of it, and someone walks up with blue-green eyes, well, you're going to have to do, you can't put them in both groups. That would be bad. That would not meet the criteria for a one-way ANOVA. Okay, so you can develop a fourth group for other, or you can decide which group they're in, or you can eliminate them from the study. And there's a host of other choices and why those are good and bad, but you'd have to make sure that they don't appear in more than one group. Okay. So again, once we've gotten to that ANOVA point, we go under Analyze, Compare Means, and One-Way ANOVA. Okay, you'll be presented with the one-way ANOVA dialog box as shown below. So this is not too different. We have a dependent list and a factor. And the dependent list always tends to go with the scale one, right? And our factor is going to be group. So we bring group down to factor and coping stress over to the dependent. I do want to point out that before you had to, for the t-test for independent samples, you had to actually, if you remember, identify your groups as 1 and 2 or 0 and 1 or whatever they were. You don't have to do that with factor. So that's kind of nice. Okay. Then you click the options button, and I'll go back in a second and show you where the options button are, and we're going to select a few things here. So here's your options button right here. Okay. And we're going to select a few things. So we're going to select descriptives, homogeneity of variance, and Welch. So descriptives are going to give us those nice means I was talking about before, so you can see if there's differences between the means of your groups. Homogeneity of variance is going to do that test for us that we need to see if we have homogeneity of variance or if our variances are quite different, and we need to run the Welch test. Then I forgot, we also want to check off a means plot. It's just kind of a nice little thing to look at to see how our groups are shaping up and how different they look. So I'll show you a picture of one in a little bit. Okay. So then you click continue, and then we're going to click post hoc next. Okay, so I'll show you where that was. Post hoc is in the center right here. Okay. So after you finish your options and you click continue next, you click post hoc. Okay. You probably are going to leave your significance level at 0.05 unless you have good reason to change it. Like if you have an alpha of 0.01, you want to change it or something. And then you're going to select Tukey. That's if we wind up running the standard ANOVA, and Games Howell in case we wind up running the Welch ANOVA if we don't meet the homogeneity of variance. Okay. Okay, so now we have to do just a little bit more work here because we want to generate an effect size. Now there is a way, and I'll show it to you, how to calculate effect size using the output, but it's a little bit, and if someone asks you to, it's good to know it, but this is easier because it just the eta squared, and that looks like this at the top, a little, it looks like an n, right, squared, will give you a nice effect size. So this time we go under Analyze, General Linear Model, Univariate. We put coping stress again under our dependent variable and group under our fixed factor. Okay. So we're under General Linear Model, Univariate, and then we just move these two over. Okay. And then we want to make sure to select estimates of effect size. Now, if you are using the school version, the RAM Cloud version of SPSS, this page may look a little bit different to you, but there will still be an option to check off estimates of effect size. Oh, yeah, and I actually included that here. So if you don't have 25, version 25, and right now the school's on 24, you'll still need to select the estimates of effect size, but it just appears down here. Okay, all right. Then you click the continue button, and then you click the OK button, and this will generate the output that you need. Okay. So let's now look at the output that we're actually getting from this procedure. Okay, so first off, we get our descriptives, which is what we like, right? These are nice, and this is going to show different levels of activity along with coping stress. Okay. So we've got our sedentary group with a mean of 4.1513, the low group, the moderate group, and the high group. Standard deviations, standard errors, confidence intervals, all this nice stuff. Okay. And it also gives us the size, the sample size for each group. Okay. All right. Here is that means plot that I mentioned before. And you can see it just does a nice job of showing you where people are. So it looks like the sedentary group has this kind of low score of coping with stress, and then it gets better as you go into more and more activity. We don't know if these, looks like there are differences here. We don't know if they're significant. We don't know if they're important. It looks like something might be going on. Okay. And so right now, all we know is that the ability to cope with workplace stress seems to increase from sedentary. We have an N, a mean, and a standard deviation, to low, N, mean, standard deviation, to moderate, to high. Physical activity groups in that order. Okay. That's all we know. But again, we still don't know if something's significant. Okay, so here is what our test of homogeneity variance looks like. You'll see the Levine statistic, and most importantly, you will see this sig value. We want to compare the sig value to 0.05. This does not depend on alpha, just like it didn't depend on alpha for the independent samples t-test. It's always 0.05 for your homogeneity variance, okay? That's just our standard. Okay. So in this case, we can say there was homogeneity of variance as assessed by Levine's test for equality of variance. And here's our p-value. Or if it did not meet it, we might have said the assumption of homogeneity of variance is violated as assessed by the Levine's test for equality of variances, and that might be a score we would have gotten, p equals 0.003. Okay. All right. So here now we finally get into our ANOVA, and we can use the standard ANOVA because we went ahead and we did met the homogeneity of variance assumption. So here's all our information. Here's the F like you're used to seeing, and here's the sig value. And of course, we know when we see a sig value like this, we report it as P less than 0.001. So now it's time to talk about reporting, I think. Okay. The ability to cope with workplace-related stress was statistically significant for different levels of physical activity. So here's how you do it. It's F parentheses. Now we're going to have two DFs. We're going to have this top one between groups, comma, the within groups. So it's between groups, comma, within groups. Equals our F value, 8.316, P less than 0.001, because we never say P is equal to 0.000. On the other hand, had there been no statistically significant difference, we would say there was no statistically significant difference in workplace-related stress score between the different physical activity groups. And again, it would have still probably been F3, 27 equals this lower number, 1.116, with a P of 0.523. And then here is in general how one might write this up. We might say that a one-way ANOVA was conducted to determine if the ability to cope with workplace-related stress was different for groups with different physical activity levels. Participants were classified into 4 groups: sedentary, low, moderate, and high levels of physical activity. There are no outliers as assessed by box plot, and data was normally distributed for each group as assessed by Shapiro-Wilk. And there was homogeneity of variances as assessed by Levine's test of homogeneity of variances. The CWWS scores increased from sedentary to low to moderate to high physical activity groups in that order, but the difference between these physical activity groups was not significant. Okay, well, we've only seen this so far. We haven't actually gotten to the Tukey's, but had we, apparently what they're saying is that even though we had this significant difference, and I think it's a good point, it could still work out that none of the groups are different from each other. That's a weird thing. Oh no, I'm sorry. This is, my apologies. This is not doing that. This is just saying the differences were not significant, and it's giving that other F statistic that we were playing around with in the last example. So sorry, what I was sharing is that on weird occasion, it's possible to get a significant F, and then your Tukey or your other one does not come out to be significant. Your post hoc does not come out to be significant. So it's a very odd situation, and it requires some thought as to how to deal with that, but it could happen. But that's not what it's saying here. Okay. Okay. So now here are our descriptives yet again. And here is our comparisons group. So this also shows the games howl was the word I was searching for, how the games howl looks. So as you can see, it pretty much looks like what I promised. There are 4 groups here, so there's a little bit more comparison. And I'll show you the next slide for the Tukey, just so you can see how you might do it. Now, I go from top to bottom. They've gone from bottom to top, but either way is fine. If you want to, you can compare high to sedentary, high to low, high to moderate, then moderate to sedentary, moderate to low, and then low to sedentary. That's all you'd have to cover, would be these 6 findings. So if you want something to kind of hang your hat on, you could say, okay, I'm only going to look at, in the second group, the first one, in the third group, the first 2, and in the fourth group, all of them. And again, we can look at the sig values, not significant for low and sedentary, yes, significant for moderate and sedentary, not significant for low and moderate, yes, significant for high and sedentary, but not significant for high and low or high and moderate. Okay. Sorry, excuse me for 1 second. Yeah, I'm in class.
Are you almost done?
Not quite, but I'll take a break soon. Okay, sorry about that. Okay, so that's where we are with the Tukey. And the Howl, I'll just go back to it, works in exactly the same way. You can see the setup is exactly the same. And you just read the rows across. Okay. Okay. And so then this is showing you a couple of those write-up pieces. There was an increase in the CWS score from the sedentary group to the group performing at a low level, and a mean increase of this amount, 95% CI of this, which was not statistically significant. And there was an increase in CWS score from sedentary to the group performing at a high level of physical activity, this to this, which was statistically significant, and there's the value. For our purposes of writing up, I would say that you only need to write up the significant post hoc ones. You don't need to write up the non-significant post hoc ones, because that would be still writing up quite a lot in even if you only had 3 to compare, and more so if you had 4 to compare. So to avoid all that write up, let's only report the significant differences. Okay. So I promised you to show you another effect size that could be calculated, and there's a reason you might prefer this, or your advisor might prefer this, but you don't need to worry about calculating it for this class. But it's omega squared, and you can see you take the SSB, or the SS between, minus the degrees of freedom between times the mean square W, over sums of squares total plus mean squares within. So it kind of looks obnoxious. It's not quite as bad as it looks, but again, I would like you to know it's omega squared, and I'd like you to know the following thing I'm about to share about it, but I'm not going to ask you to calculate it for this class. But it's good to know in case like you have to do it for your dissertation or something. So as you can see, here is where you get the eta squared, and you just go in the test of between subjects effects, and you'll see under group, if you go across, partial eta squared, and it's 0.4 eta. That's what you want to report. And so the only difference really is that this is a measure of effect size in the sample, whereas omega squared represents an effect size in the population. So might be slightly better, but this one's already calculated for you, and I think it's sufficient. Okay. And here is our longer write-up, including basically everything. So the first part we've already talked through, I believe, with the F and the that part. And here you can see I'm just going down to the second half where they're reporting the P. I would report an exact P rather than P less than. You can, but I think the exact P is just as good. And the only time to report less than is if it's 0.000, and then you're going to say P less than 0.001. They report the omega squared. Again, you can report the eta squared. That's perfectly fine. And then they report the differences between the groups. And then they report the Tukey post hoc analysis revealed mean increase from sedentary to moderate was statistically significant, as well as the increase from sedentary to high. But no other group differences were statistically significant. Just as I was sharing before, you only really need to share. So I really like everything about this write-up, just to make it easy. I like everything about this write-up except you can do eta squared, which I think is easier. And I would report the exact p-value for your F test. Other than that, I think it's a great model. Okay. And then finally, I I just want to show you what the Welch looks like in case you don't have homogeneity variance. We did ask for it to print out. So what you would get is, this is your F, 14.821. This is your first DF that goes at the beginning. This is your second DF that goes second. And here is your p-value, which again, I would have reported as p equals or t less than 0.001. I guess they wanted that extra zero in there. They were greedy. Because I think that's why they reported as p less than 0.0005. So maybe that's what they were doing there. Okay. So I know there's a little bit of red and blue and kind of craziness going on, but hopefully you can see where all the numbers come from. DF1, DF2, your F statistic, and your sig value. Okay. And then this would be how you could write up a one-way Welch ANOVA. It's pretty much the same as what we've been looking at. I think the only difference is you would say, of course, that there was heterogeneity of variances as assessed by Levine's test of homogeneity of variance, or you could just say that the Levine's test for homogeneity of variance failed, and you report the p-value. And then you report the Welch's F, just like we talked about. Okay. And this goes on again to show you the differences between the groups. So good thing to look at for the Welch. Okay. So this is where we would get into the Kruskal-Wallis test, but I think it's a good time for a break. Then I want to briefly discuss the Kruskal-Wallis test and then give you an option as to what you'd like to do after that. And there'll be a couple of options there. So you can think about it. We could either be quite done. We could do a couple of practice problems either together or individually, or which wouldn't take long, especially if we did it together with my walking you through one of these kind of step by step. We could do that, or I could go through. Probably, I don't know if there'd be time to go through part 1 and part 2, but I could probably go through one of the parts and talk about the test a little bit more, something like that. And there might even be time for more than one of those activities. So keep that in mind for after, because the Kruskal-Wallis part is not nearly as long. So let's take a 10-minute break. And I need to skedaddle for just a minute, but I will be back if you have any individual questions for me. Okay, so I'll see you in 10. Oh, there is a question. Oh, yeah. Yeah, that's another option. We can definitely do that. Okay, I'll keep that in mind. I'll offer that as an option too. Thanks for bringing that up. Oh, that was private. Sorry. Hi, sorry about that. I was on mute. Someone just told me. So I was just saying, if you're back and I haven't seen you wave yet, would you please wave or do something so I know that you're back? Thank you, Justin. Ryan, okay, so I think we have everyone. Perfect, thank you. Okay, let me do a couple things here and then we'll, there we go. Okay, so I want to talk to you a little bit about the Kruskal-Wallis test. So let me do that, and then let's check in and see what we'd like to do with the remainder of the time. One suggestion that came up over break, which I thought was a good one, is, you know, even if we don't review the test tonight, we could review it next time once you've had an opportunity to look at your scores and your grades and those sort of things. So we could, that's another thing for the table just to put on there. We could do that. And like I said, I'm happy to do it individually with you. Just grab a time with me. Either try OneTub, but if that doesn't work for you, then just email me and we'll work something out. Okay. So let's check in about Kruskal-Wallis and then I'll check back with you and see what you'd like to do. So I think that'll be a good decision time. So as I mentioned, the Kruskal-Wallis test is an alternative to the ANOVA. And we use it when we haven't met one of the criteria for ANOVA, such as a substantial departure from normal distribution or significant outliers are present. Okay. So this just shows that we have a potential deviation from normal or potential outliers, that kind of situation. So this is okay, but I decided I don't really love it. So what I'm going to do is I'm going to do a new share if this works. Give me 1 second to get to where I want to be. There. Which is under Kruskal-Wallis procedures under layered. So the way we want to approach this, I think you can all see that. If you can't see the layered thing in front of you, just let me know. The way we want to start in is go under non-parametric tests, independent samples, just like we did for the Mann-Whitney. You can choose this to automatically compare distributions across groups. That's fine. And then under fields, we're going to put group under our groups and coping stress under our test field. And actually they make a good point to look here, look in the little red boxes to see what kind of variable it will accept. So in other words, your dependent variable, your test field, if you will, has to be a scale variable in order to go. The group is more flexible, but this, make sure it's coded as scale. Okay. Yeah, and that's kind of what they're pointing out throughout here. Okay. So we moved the independent variable over and the dependent variable over. That's great. If you had a second dependent variable, which we're not going to get into for quite some time, you could move that over as well. But you can ignore that for now. Okay. Under settings, they even point out that you could just leave it automatically or you could customize the test. I prefer to customize the test. So I would probably go ahead and click Customize Test and then click Kruskal-Wallis. And I should have, sorry, this is Kruskal-Wallis page 7 if you're looking for a reference. So sorry about that. Okay, so we brought that over. Yep, we did the customized tests and Kruskal-Wallis. So far, nothing is too crazy or too different, I don't think. Under test options, we pretty much are going to leave this significance level and confidence level alone unless we have an alpha of 0.01 or an alpha of something different. Then we can change that. Now, this is an interesting point that they bring up about missing values. So you see here, exclude cases test by test or list-wise. And I'm just going to point this out to you because it's worth noting, because I suspect some of you might be doing something a little more complex for your dissertation, and it's good to know the difference between these two. So basically, let's say we did have two dependent variables, coping stress and engagement, okay? Notice how for coping stress, we're missing this case right here, case 8, I believe. And for engagement, we're missing this test right here. Is that, I'm sorry, I'm not doing a good job of going across. I believe that's 11. So if we had done it with the case, with the test by test, sorry, let me go back to that. Exclude cases test by test. Then when you ran the test on coping stress, it would only leave out 8, that one person. And then when you ran the test on engagement, it would only leave out person 11. However, if you had chosen the other way and you had said exclude cases list-wise, then it would leave out 8 and 11 for both tests. Now, why, you might be wondering why you'd ever want to do that. Yes, this is also true for ANOVA. Yeah, that was a good question that just came up. Is this also true for ANOVA where you can exclude cases, test by test or case or list-wise? Yes, and it's the same answer. It's the same choice. And for all the tests, frankly, you can always choose how your missing values are done. So yes, always you can choose whether it's test by test or case or list-wise. If it's list-wise, like I said, it would leave both out. Now you might be first thinking, well, I'd like to capture as much data as I can. Why would I leave both out? And the answer that you might come to is that when you're writing up your results, sometimes it's easier to write your results about a set group of people. So let's pretend that there are 50 people total. And in the case, you'd have to write up your coping stress with an N of 49 and explain that this is different from the N of 49 that you ran for engagement. And that can be a little bit not desirable because you're running your tests on different groups of people. Now, if it's only 1 and 1, it may not be such a big deal, but you can imagine if you have more cases missing, how it can become a bigger deal. So I always recommend doing it list-wise, even though you lose a little more data. I think it makes the interpretation more straightforward. Yes, and good question. That is true for any test. Okay. And then we're going to run this and hope it doesn't. Yeah, I knew it was going to do that. Sorry, give me one sec. I don't know why it constantly wants me to re-sign in. Okay, back to our Kruskal-Wallis, and we'll be up to page 8. So let me just skip ahead to page 8 so we can actually look at how to generate the medians. So I showed you one way to generate the medians, and it still works. And in fact, I I personally like it because it's already, you already have done it. And that's when you run your descriptives explore at the very beginning to even decide if you're going to do your Kruskal-Wallis. It'll give you medians right there. So you can use those, or you can use this technique for generating medians. So you go under compare means, you put your dependent and independent in the groups. And then you go under options. So again, compare means, under analyze, compare means, put your dependent, independent in the group, go under options, and then just bring over median. You can get rid of the mean and standard deviation. You don't really need that. You can leave it. It doesn't matter. Just all you really need is the median. And I would keep the number of cases as well. So median and number of cases. Click continue and you click OK. So it's up to you. It's a little bit maybe easier to read if you do this than having to search back through the Explorer for the medians, but both will work. Okay. Then we start getting into seeing some of the results. This wants us to reject the null. We've got a significance value of 0.002. When we look more deeply at it, we can see how we can get some more information about the total N, the test statistic, the degrees of freedom, and the p-value. Again, this does want you to look at the shape of the distribution to make sure that you're okay to do the Kruskal-Wallis. Again, if this was a dissertation type thing, maybe I'd say, yeah, go ahead and look at that. But I think for the purposes of this class, I mean, even for dissertation, I think that's going a little deep. I think if you have already gone through the ANOVA and realize you need to run a Kruskal-Wallis, I think the Kruskal-Wallis honestly is robust enough that even if it's not perfect, the shapes of the distributions, that you'll still be okay. But this is a nice description of how to deal with that. Okay. So yeah, so I would say continue on, assuming that your distributions are okay. Okay, and then we can actually start interpreting results. And we're, like I said, we're going to assume that we have similarly shaped distributions, which means we're going to look at medians. So let's compare our medians. Okay. And this is just showing you if you don't have a significant result, what that looks like. It says retain the null, but I think you're used to that already from the other tests we ran. But in this case, we're going to reject the null. And we can see initially how we might write this up. A Kruskal-Wallis H-test was run to determine if there were differences in the CWS scores between 4 groups of participants with different physical activity levels, sedentary, low, moderate, and high physical activity level groups. In this case, we're saying the distributions were similar for all groups as assessed by visual inspection of the box plot. Again, we can assume that median scores were statistically significant different between the groups. And then it's a similar reporting. It's not exactly the same as the F. So let's make sure we know how to pull all this information. We've got, we're basically reporting it as a chi-square. That's what that little funny X is. It's chi-square with 3 degrees of freedom equals 14.468 and P equals 0.002. So here is the 3 degrees of freedom, the 14.468 we're reporting, and the p-value. So it all pretty much is there. And it's a little bit, in my opinion, slightly easier to report this than the F-test. Okay, all right. And then, of course, these are the medians that would come out if you had done the mean approach that they said before. And you could look at the reporting for that, whether you have significant or not significant. But it's very similar to what we talked about so far, where you can report the actual medians for each group. At this time, if you're reporting medians, of course, we do not report standard deviation as in the other group. So you can see that right here. We just report the medians. Okay. And then the post hoc test, right? Because we got to have one of those. This is where it's a little bit different and a little bit funny. And so what you want to do is you want pairwise comparisons, okay? So you can view the pairwise comparisons that have been run by SPSS Statistics by selecting pairwise comparisons from the drop-down box. Okay, so you see that down here. You're just going to choose pairwise comparisons. Okay. And then it will give you this. So I think it's actually technically a little bit easier to read than the Tukey or Games Howl, because it actually only gives you each one once. So that's kind of nice. And it actually gives you a graph as well, just to show you what's different, to show you what looks different anyway. So we can see that sedentary to low is not significant, but sedentary to moderate is significant. And you do want to use that adjusted sig value over here on the right. Sedentary to high is significant. And then the rest are not, as you can see. Okay. And again, just like before, everything we're doing two-tailed, everything we're doing assuming non-directionality and alternative hypotheses. Okay. So this is just going through that in some detail, but that's the basic idea here. Okay. And then this next part, I would say, if you're going to read this again, skip this. Comparison of distributions and descriptors for distributions and post hoc test distributions. And then I would just skip ahead to reporting. And of course, as always, go over to the APA side. And this is just giving you a choice as to do two different ways to report the results. Basically, the first part is very much the same with reporting the ends, saying what we did, saying why we did it. So they're both pretty good in terms of how you'd actually attack that. The only thing I would say is I would cover the first part of mentioning, that it failed to meet the criteria for either normality or the box plot, whatever it missed that told you to do the Kruskalj-Wallis in the first place. Okay. And then we can ignore the bottom part, because this is if you're doing distributions with a post hoc test. We're going to be doing medians with a post hoc test.
Dr. McKibben, I just have a question.
Sure.
So when we're doing the one-way ANOVA and when we're doing the Kruskalj-Wallis test, you said we're not assuming a direction, we're just looking for group differences?
Mm-hmm.
Okay.
Yeah. Yeah. We're not going to worry about one-tailed and directionality. Now, there is a way to do that, and I want to show you one thing in just a second. Yeah, I don't want to show you that, but what I do want to show you, since you asked that, well, I was going to show you anyway, but let me just show you this. I'm flipping over to the one-way ANOVA, and I just want to show you that to the right, there's the Gaines Howell, carrying out simple and complex contrasts and custom contrasts. There are ways to approach this one way, this one tail type thing, but we're not going to worry about those. So if you're again reading this, I would skip all the stuff about the custom contrasts and just skip over to number 26, the reporting. Okay. All right. That covers what I wanted to cover. Here are the choices. We have an hour to play with. If your brain is full and you're done looking at this entirely, we can call it a day. At least some of you can call it a day, or however you want to do that. I have set up a couple of data examples that I can either run through, or you can run through individually, however you'd like to do that. or I can talk a little bit about the exam, or like I said, we can talk about the exam next week or individually. So, let's see, how do you want to do this? You want to, let me see if I can pull this back out so I can see everybody. Give me 1 second. I think I got most of you, but not everyone. Okay, that's better. So
I think that I agree that it would be helpful to talk about the exam like after I can see the feedback and my grade.
okay, fair enough. Is that where most of you are at? Yeah. Yeah. Okay, fair enough. Okay, so let's not do that. So then what I'll do is, at least for those of you who are interested, let's do the the practice ones. So then my next question is, would you rather see me do them, or would you rather take a stab at doing them? Any votes there?
Well, can we like revisit the conversation that we were like what you were sharing with us in the beginning of class?
Yeah. Oh, you want to revisit that? Sure. Yeah. You mean about like how you want to structure like the actual class time, and like whether it makes sense to like listen to lectures in real time or listen to them on your own?
Yeah, because I don't know about everyone else, but I feel like for me, like now my brain is fried. So I just feel like for myself, it would be helpful if I could hear the lecture part before class and then use class time to do the practice problems together and ask any questions that we have. Because I feel like, I mean, some of us were talking, and I feel like a lot of us are meeting with you individually to ask questions that like we could ask in class if we were like doing the problems, if we had already done the problems, and like watched the lecture. And I don't want to waste like a lot of your like personal time answering the same questions.
Yeah, I understand. And I hadn't thought of it like that, in the exact way you just put it. So that's interesting. I know we did talk about the topic, but I was thinking of it slightly differently, but that's a good option. So I could always record your lecture. I guess I'd have to say I'd record it on the weekend, and so it would be available like on Monday at the latest. If I got to it like, on Sunday, it might happen Saturday, it might happen Sunday. So then you'd have access to the lecture Monday. Does that give you enough time does that make sense for you guys? Do you want that so that then you can just listen to the lecture on your own and come here with questions and work through problems and that sort of thing?
That will work for me.
Okay.
Yeah, I kind of want to try that and see how that works, because same like Lindsay, like I feel like Wednesdays by this time, like it's hard to keep up. My brain's fried too.
Yeah, that's fine. We can definitely do that. Are there folks, although I can't do both. Like I was trying to think of a way to do both. I can't do both. So I guess we need a true vote here, a majority rules, and there's 8 of you. So let's hope it's not 4 and 4. So can you just like wave or raise your hand if you'd like to do that option? 1, 2, Lindsay, Korea. 5. Okay, good. We have 5. Okay. Okay. Perfect. Okay. All right. So there's only one person I think who didn't raise, and that's fine. If that's a real problem, let me know. And we'll put our heads together and think about it. But since the majority rules here, we'll do that. Okay, we'll start this weekend, and I'll record the next lecture, which will cover more about different kinds of ANOVA, and do that. And so if you are done, so I think that's the plan. We'll do that. I'll record this weekend. I'll put it up there on YouTube. You know where to find it. on my channel, on my playlist for this class. If anyone's having trouble finding my lectures, just let me know and I can point you in the right direction. We'll try it for this week, and we'll see how that goes. And then we'll come in next week, and then we can just use the time, since we'll have more time. We'll do our 2 article reviews, right, for both dependent samples and for the Wilcoxon. And we'll do some nice SPSS together for both, probably what would have been for this class, for the ANOVA, the Kruskal-Wallis, the repeated measures, etc. So we'll cover, I think we'll have the time to do it if I won't be lecturing in class.
Thank you so much for being like flexible and accommodating. We really appreciate it.
Yeah, no, I understand. I want this to make sense for you. And honestly, it's perfectly fine. I have done some of my other classes like that, and I kept this one because I thought it would be more important for you to like have the live experience, but I'm totally fine with the other way. So that's great. Let's try it out. If anyone is interested in sticking around to ask me questions or anything, please feel free to do so. Other than that, since it sounds like some of you are fried already, then please have a good night, and I'll see you next Wednesday.